I'm Donna Young, the National Science Olympiad Astronomy Event Supervisor. And this presentation is an overview of the content and resources for the National Science Olympiad Division C 2025 astronomy event. The national competition will be held at the University of Lincoln, Nebraska. There is also a transcript that includes links for most of the slides. The links will provide you with 1 to 3 websites to access that will give you a starting point for collecting information about the content and the deep sky objects. You can download both the PowerPoint slide set and transcript in PDF format from the NSO website. The recording itself will be posted on the Chandra website with links to NSO and to the Universe of Learning Universe Unplugged Science Olympiad page. The space science events, astronomy, Reach for the Stars, and solar systems are all supported by the Universe of Learning program. It is a unique partnership among the Space Science Telescope Institute in Hubble, the Smithsonian Astrophysical Observatory in Chandra, the Caltech IPAC missions like Spitzer, and the JPL. Each of the partners have their own individual networks for additional partners, and one of Chandra's partners is the National Science Olympiad. This webinar has 4 parts: a basic understanding of the content, and is necessary to understand how exoplanets form and how the motions and physical properties of stars and exoplanets provide us the ability to detect and study them. The last segment will focus on locating the resources and some suggestions on how to prepare for the event. This slide shows the first part of the event description for astronomy. The only change in the event parameters is a statement that AI tools, such as ChatGPT, are not allowed under any circumstances. Otherwise, the same resources apply. Each team can bring 2 laptops, 2 3-ring binders, or 1 laptop and 1 binder. Because JS9 is now browser-based and works exceedingly well, we try to have the astronomy event held in a computer lab whenever possible. This makes the JS9 question much easier, as the website will be active during the entire event, so teams can work on the JS9 question at any time during the session. If a computer lab is not available, teams will access the NASA JS9 website on their own computer or tablet. If you do not have a laptop, the event supervisors will provide one for you. I do not know yet. The rooms have not been assigned for the national event yet, so I do not know for certain we will be in a computer lab yet. Under the competition, number 3, that lists the tools and the concepts that are necessary to understand stellar evolution and orbital mechanics in parts 3A and 3B. The words in red in the competition and 3A are all closely related. Those are not terms that are new for this year's event. They are simply ones that are all so very closely interrelated and also relate to some of the content in 3B. Understanding how they are all related, how they are all involved and affect each other, is what you need to understand to have a solid foundation. So, stellar evolution is a process. There are 4 different segments: stellar evolution, the deep sky objects, the HR diagram, and the light curves are the 4 segments involved with stellar evolution, the entire process. Those segments should not be treated as separate topics to learn, but an integrated portrayal of the entire process. Teams think they need to learn about the deep sky objects and the light curves and the HR diagram, and they treat them as separate topics. instead of different methods of learning about stellar behavior during the transitions onto and off the main sequence through instability strips to other branches and the final stellar end products. The illustration on the upper left is an artistic view of the HR diagram. The graph on the lower left is basically a plot of some combination of physical characteristics of stars: temperature, classification, luminosity, and/or absolute magnitude. The image on the upper right of this slide is M42, our good friend, the Orion Nebula. It is one of the deep sky objects for this year's competition, and I will discuss it when we get to the deep sky objects segment. For a basic walk through stellar evolution, there are introduction and background materials on the Chandra website that is a good beginning. It will say that those materials have been archived with a warning that it is no longer being updated, and some of the links might be broken. I've gone through the introduction and background on the Chandra website, and right now all the links are working fine. There are a multitude of different HR diagrams, and there are many ways to construct them, depending on what is being emphasized. There are, of course, some misleading and incorrect ones, some outdated ones, so it's important to understand the graph. There are also several videos and interactive websites that work well to increase understanding. This slide shows 3 different HR diagrams that have been used for questions written for invitational, regional, state, and national competitions. The HR diagram is a plot of the temperature/stellar classification and absolute magnitude/luminosity of a star. The location of a star on the HR diagram is a plot of its current stage of evolution, providing the age, mass, composition, and evolutionary past and future of the star. Absolute magnitude is the intrinsic brightness of the star, and luminosity is how much power the star is emitting relative to the sun. The sun is arbitrarily assigned the value of one solar luminosity, and other solar luminosities are relative to the luminosity of the sun. The sun's position on the HR diagram is plotted at 1 solar luminosity and approximately 6,000 K, which corresponds to a G2 stellar classification. Objects plotted on the HR diagram change position on the diagram as they evolve, though the stars themselves do not physically move. Look at the 2 HR diagram illustrations. The illustration on the right has an extra line at the top that is not on the illustration on the left. This is because that stellar evolutionary stage only existed in theory until the Chandra mission discovered a supernova event that supported the theory, and this type of event is no longer theoretical. It is a depiction of a star so massive that it has used up its core hydrogen by the time it reaches the main sequence, and the implosion produces matter and antimatter, which annihilates each other, and there is no remnant or stellar core left behind. The star transitions from formation to collapse in such a short time that it's amazing such an event was ever caught while it was happening. The stellar classifications on the middle and right show different classifications. Looking at the 3 HR diagram plots, again, the one on the right shows absolute magnitude, luminosity, temperature, and stellar classifications, OBAFGKM. The middle graph has classifications C and S after M, and the plot on the right is L and T after M, as well as the B-V color index above the classifications. There are many classifications besides OBAFGKM. Basic information about stellar classification is provided in the 2 Chandra links in the transcript. For in-depth information about stellar classification, the following attached link for the Wikipedia article is a great website. Wikipedia also has a good explanation of the B minus V color index, which is a measure of a star's color, which is an indication of its temperature. The UBV system classifies stars by spectral type based on photometric measurements of the ultraviolet, blue, and visual magnitudes. Hot stars appear bluer than cooler stars. Cooler stars are redder than hotter stars. The B minus V color index is a way of quantifying this using two different filters. One, a blue filter, B filter, that only lets in a narrow range of colors or wavelengths, those centered on the blue colors, and a visual filter that only lets the wavelengths close to the green-yellow band through. A hot star has a B minus VN color index close to 0 or negative, while a cool star has a B minus V color index close to 2. Other stars lie in between. There are 4 links in the transcript for really good basic introductory material on these concepts. This slide shows, again, different HR diagrams can have stellar classes besides the ones that you usually see. The graph on the right is an interesting diagram and shows where stars in different stages of evolution are located. The diagram on the top in the middle was produced for the plotting pulsating variable stars on the HR diagram activity. The answer key below it shows how variable some of these pulsators can be as they transition from one branch to another. This activity is posted on the Chandra and the AAVSO websites. This year, we do not have a lot of light curves due to internal things that are going on underneath the surface of the star, but we have more light curves that are basically extrinsic to the star, where you have one object moving in front of or back of another star or exoplanet that it's orbiting. However, there is always some kind of variability, light curves on just about every single event, because light curves are very important to help you understand what's going on internally within the star itself. So let's review the content listed in parts 3 and 3A of the event description. We have looked at a majority of the topics listed in this section. The next 2 slides will show the locations of different classes of variable stars and their associated unique light curves. The AAVSO and the Australia telescope have good basic information about variable stars. So as you can see, we've talked about the process of stellar evolution, which includes light curves, motions. We haven't gotten to the distance equations yet. We will. The stellar magnitudes, classification, multi-wavelength images. It's very important with deep sky objects to get observations done for each of the different forms of radiation. You just don't know what's going on within a star unless you see it in X-ray, UV, optical, infrared, radio, because every one of those wavelengths is produced by a different process. It's sort of like if you want to understand how a human organism, a human being functions, you can't just learn about the gastrointestinal system or the nerve system or the digestive system or the skeletal system or the muscular system. You have to learn all of those different things and how they all integrate and work together for a human being to function as they do. So multi-wavelength is always very important. The stellar evolution is also, we have classification, spectral features, chemical composition, luminosity, color index, HR diagram transitions, even the protostars, Herbig Haro objects, T-Tauri variables, Herbig AEBE stars. Those were on last year's competition, because last year we were focusing more on pre-main sequence stars and protostars. And this year, we don't have any deep sky objects that fit those categories because if you will have noticed, if you've started studying, that this year's stars and exoplanets, the exoplanets are orbiting stars that have already reached the main sequence. Most of them are M, K, G stars, and 2 of them have actually gone through their entire evolutionary sequence, and they are now stellar cores. It's important to know what came before the main sequence, and those of you that studied for last year's competition will be familiar with those already. The exoplanets this year are Neptunes, sub-Neptunes, super-Earths, and terrestrial planets. So this slide shows the location of 2 types of protostars as they transition from the collapsing clouds of gas and dust onto the main sequence, and their position on the HR diagram is determined by their mass. When the object is hot enough for core hydrogen to fuse into helium, it joins the main sequence. Their light curves are very erratic because this produces an awful lot of energy, especially in the X-ray and ultraviolet parts of the spectrum. This slide shows the location of the instability strips as the variable stars transition from one branch to another, because while they're in these stages of instability, some of them produce a periodic light curve as they fuse heavier and heavier nuclei. These light curves are used to measure cosmological distances. The Cepheids, the R Lyrae, the Mira variables. There's also a group of semi-regular variables. Each class of variable produces their own unique light curve, and their cycles range from less than a day to 300 and more years. So again, these are all produced by internal processes, exotrinsic properties of the stars as they become unstable, moving from one stellar evolution phase to another. And I know a lot of this information is basic for those of you who have been competing for the past few years, but remember, some of you are competing for the very first time this year in astronomy and therefore don't have the same knowledge base. So I apologize if you think this is too simplistic. So the period luminosity relationship and the distance modulus are relationships that are used to calculate distance. And as you can see on this graph, the distance modulus, which is the absolute magnitude of the star, is equal to its apparent magnitude minus 5 log 10 r over 10. So if you know the absolute intrinsic brightness and you know the apparent brightness, you can determine its distance. And they produce a very unique light curve because you can, again, you can also use the magnitude of the sun minus the intrinsic magnitude of the star, again, is equal to, has a relationship with luminosity. So the period luminosity relationship shows the relationship between the period and the luminosity. And you can see for like R Lyrae stars, they pulsate every 0.72 days. They don't even take a full day, where the Cepheids have a period that can take them all the way to more than 100 days. So remember this, there's always going to be variable stars and light curves on our events, for astronomy anyway. Of course, also for Reach for the Stars, and I'm sure solar systems, because there's a lot of variability in that one too. That was sort of a brief walkthrough of understanding a bit of the content, why it's part of the event description, why it's important. A lot of these topics never change. They're pretty much there because they're important to know and understand. We are now going to move on to part 2, which is everybody's favorite, understanding and studying the deep sky objects themselves. Part 2 summarizes the deep sky objects for the 2025 tournament year. A lot of time and energy and other factors go into the decision for the deep sky objects each year. We consider the range of major missions that are involved. because we need to see multi-wavelength observations, their history. Some are kind of like historic, first evidence observations, changing knowledge as image analysis and technology changes. So sometimes you discover that what you thought you had discovered before isn't valid anymore because there's always ongoing increasing technology that allows us to even find exoplanets in materials and observations that have been around for a long time, but we haven't had the resolution to show them up yet. We have representations here of different types of exoplanets, different stages of evolution for the parent stars. The exoplanet scientist, we look at what they are doing. And of course, we have our own A-team experts, Andrea and Tad, who both are focused on exoplanets and their atmospheres. And then there are the just plain fun objects that are really unique for some odd and unusual reasons. All of these things are weighed for consideration. So it is up to you, of course, to study and understand this year's deep sky objects. So the following slides are just a brief summary, mostly to give you a feel for the overall content and maybe some especially interesting information that makes them unique. So the DSOs on this slide are colorized by the type of DSO that they are. Now, this is a purely arbitrary grouping on my part that I find useful for myself so I can present them in at least some kind of organized list. It is arbitrary, though, but hopefully it's not random. You will see as we go along that one difference between the 2024 and the 2025 DSOs is that, as I've mentioned before, most of the parent stars have either arrived on the main sequence or they're orbiting stellar cores. None of the stellar objects are T Tauri or Herbig-Haro objects. Everything is pretty much post-main sequence. However, if you competed in astronomy for the 2024 season, you will have a good foundation for the formation environment for this year's exoplanets and their parent stars. I absolutely love this animated sonification, which shows the number and locations of exoplanets and their methods of detection from the very first one detected in 1991 through 2022. Later on in this segment, we will look at the missions, past and present, that detected these exoplanets. There is a link to this animation in the webinar transcript. See, it's also giving us the method by which they were all detected also. So, as you see, now that we have all of the exoplanets up, you could see that most of them were found by direct imaging and radial velocity. We'll talk a bit more about that later. This slide, look at this. Okay, how can you not love the Orion Nebula? We've had it as a deep sky object several times. I love this particular image of it, which is actually observed by a ground-based telescope. It's a star formation region that's only 1,500 light years distance, detectable with the unaided eye. It contains a large range of objects, from the young massive blue stars forming in the trapezium to a collection of failed brown dwarfs and low-mass stars. It has all the usual activity associated with this type of region, including cold molecular clouds, collapsing clouds of gas and dust, and emission and reflection nebulas. It has been observed by several missions in all wavelengths, including ground-based, as this one is. So there is a wealth of observational data for Orion. The image on this slide was collected using the Hawk-1 infrared instrument at the Very Large Telescope in Chile. Oh, and there's also, of course, the fascinating mythology that goes along with Orion the Hunter, the Pleiades and Taurus, the dogs, the charioteer. It's a pretty cool nebula. And this image was on the very first page of this webinar. And 30 Doradus is also a star formation region. This one is located in the neighboring galaxy, the Large Magellanic Cloud. It's also known as the Tarantula Nebula. It is the largest and brightest region of star formation in the local group of galaxies. This region has also been extensively imaged by missions in every wavelength. I like the image on this slide, as the background image is the Chandra Hubble-Spitzer composite, and the highlighted region a Chandra JWST composite. This is just a really nice image to show why wavelengths from one end of the spectrum to the other need to observe and study deep sky objects. The hot Jupiter exoplanet, HD 80606b, is orbiting a stellar classification G star. As you know, this is the classification for the Sun. So when the star is run out of core hydrogen, it will become unstable and transition to the red giant stage through the Mira variable instability strip on the HR diagram and collapse into a white dwarf, puffing off a little planetary nebula. HD 8066b is in a highly eccentric orbit, taking 100 days away and then back to the exoplanet in 20 hours. It just whips around the star at its closest approach to it, nearly touching it. If the Earth was that close to the Sun, it would lose its atmosphere, and its surface would be magma. The exoplanet heats up to 1400 K, then in 10 hours cools so much that the Spitzer telescope cannot detect it for the remainder of its orbit. WASP 17b is a very unusual exoplanet. WASP is the catalog for the Wide Angle Search for Planets project. It is an international group of several organizations searching for exoplanets using transit photometry. It is tidally locked and the first planet to have a retrograde orbit. It is half the mass of Jupiter, and 1 year is the equivalent of an orbit of 3½ Earth days. The radius is 7 times greater than Jupiter. The surface temperature is 1550 K, which is hot enough to melt nickel and lead. The YouTube link that's provided in the transcript shows the details of WASP 17b. Note that the exoplanet is orbiting an F classification star, again similar to the Sun, thus giving you the history of WASP 17 from pre-main sequence through formation. Like many other hot Jupiters, WASP 121b has shown evidence of heavy metals. Observations have shown evidence that magnesium and iron gases are escaping WASP 121b due to the extreme heat. Again, as in WASP 17b above, the host star is very similar to the Sun's position on the HR diagram. The temperature is 4600 Fahrenheit. It is so close to the parent star that it only takes 1.1 days for one orbit. And you thought 3½ days for WASP 17b was short. Tidal forces will eventually destroy WASP 121b. This was the first exoplanet atmosphere observed to have water in its atmosphere. And if you thought the 2 WASP exoplanets had short orbits, take a look at ultra-hot Neptune-like ice giant LTT 9779b. This is the only exoplanet in this category, and like all hot planets, is not expected to be visible in the UV or optical part of the spectrum. However, this exoplanet has an unusual high albedo, and TESS and CHEOPS observations show evidence of scattered light from its atmosphere. Clouds should not exist on this planet. This exoplanet has an orbital period of 0.8 days, Its parent star is the same stellar classification as the Sun. It is a G-class star. K2-18b was a really exciting discovery, as a significant amount of water vapor was detected in its atmosphere. And though the exoplanet is significantly larger and more massive and orbits a cooler Class M red dwarf star, it orbits within the habitable zone. The water vapor was detected by Hubble, Spitzer, and Kepler. After further observations with JWST, other life-indicating molecules, including carbon dioxide and methane, were also detected. Other studies have questioned this result. The YouTube link that I have provided in the transcript gives a detailed summary of the observational data. It's really very interesting. Like K2-18b, TOI 270d also orbits a Class M red dwarf star. However, unlike K2-18b, exoplanets like TOI 270 are good candidates for life within or even outside of the habitability zone. The term Hycean planet is used to describe planets that have large oceans and hydrogen-rich atmospheres. Hycean planets are thought to be common around cool red dwarf stars. Any life forms would most probably be aquatic. So a caveat here would be that the first confirmed exoplanet was 32 years ago, and our ability to detect, confirm, and study exoplanet surfaces and atmospheres has certainly grown exponentially over the past few years. I've enjoyed having exoplanets be the focus of the astronomy event. I've tried to present recent research observations and results. It is a field that is constantly changing as more data is gathered. Always interesting. The links that have been selected hopefully present the most current results. However, even if it is, conflicting results can negate current theory at any time. I try to use the words likely, possible, current thought, or theory as information changes so rapidly, especially in the exoplanet field. The Class M red dwarf star, GJ 1214, has a super-Earth exoplanet, GJ 1214b, orbiting it. Super-Earth planets have a rocky surface and are significantly more massive than Earth, but much lighter than ice giants such as Neptune and Uranus. The planet is too hot to be habitable, however, likely contains atmospheric water vapor. These planets are thought to make up the majority of the exoplanet population. JWST has recently observed GJ 1214b and has produced the latest information about this object. Upcoming missions will have the ability to study super-Earth exoplanet. LHS 3844b is another super-Earth exoplanet orbiting a red dwarf parent star. It has a diameter of 1.3 times the Earth, and its dayside temperatures reach 100 degrees Fahrenheit. It was detected by the TESS mission. JWST has planned observations of the planet's thermal emission spectrum with the MRRI instrument to determine the composition of the surface. Okay, PSR B1257 plus 12 system consists of a pulsar and 3 exoplanets. These exoplanets were the first extrasolar system planets discovered by radio astronomers at Arecibo. How these exoplanets formed is not understood. They could not have formed by the massive supernova event that resulted in the pulsar. It is thought that they could have formed from a disk of stellar material that fell back towards the pulsar after the supernova event. The constant bombardment of high-energy radiation that rains down on the exoplanets from the pulsar are certainly not conducive for life. Another hostile environment. The white dwarf, 1856 plus 534, is a triple star system comprised of a red dwarf binary pair gravitationally bound to a white dwarf with a giant gas exoplanet. The collapse of a mid-sized star into a white dwarf would destroy any nearby planets. An object or material would be torn apart by the strong gravitational field if it approached the white dwarf. So this exoplanet might well be an extremely rare survivor planet, as it is only 9 AU from the white dwarf. The 55 Cancri system gives evidence that planetary systems similar to the solar system can exist. 55 Cancri is a type K star and a binary system with a red dwarf and has 5 orbiting exoplanets. One of these planets, the super-Earth 55 Cancri E, has a molten surface of lava, and like the moon and Earth, it is probably tidally locked with 55 Cancri. JWST observations indicate that energy is being distributed from the day side to the night side because of the lower than expected temperatures. Currents of lava cannot account for the amount of heat transfer to the night side, though. So the link to this object gives some very interesting information. The Kepler 62 system, like the 55 Cancri system, consists of a K-type star and 5 exoplanets. However, the similarity does end there. 2 of the exoplanets, Kepler 62e and Kepler 62f, orbit within the habitable zone, and the Kepler 62e is close to the holy grail of a habitable Earth-like planet. Modeling by the Harvard Center for Astrophysics suggests that both planets are water worlds, with their surfaces completely covered by water, no land in sight. Any life would be underwater with no access to the physical elements and properties that could lead to the formation of life as we know it. The AU microscopy system is only 23 million years old. An AU Mike is a K-type red dwarf, the most common type of star in the Milky Way galaxy. Studying this system will provide a lot of information about how planetary systems form. The star is still producing high-energy flares of radiation, which is stripping the planet AU Mike B of its atmosphere. Researchers believe they are observing essential evolutionary mechanisms that most planets go through, which will allow us to understand the extremely early stages of planet formation and how the solar system formed. One of the links is a Dartmouth article that describes the research on this object extremely well. Epsilon Eridani is only 10 light years distance. It's the only one that is that particular distance away, except, of course, for Orion, that would probably be the closest one. The thing about Epsilon Eridani is, and it is the third closest naked eye star too, so it can be seen naked eye. It is about 800,000 years old, which is approximately the same age as Earth when life started to form. Epsilon Eridani also is surrounded by a belt of comets, similar to the solar system's Kuiper belt. The system also has 2 asteroid belts, one at about the same location as the solar system's asteroid belt, and one much more distant one, around the orbital distance of Uranus. Exoplanet Epsilon Eridani b orbits exterior to the first asteroid belt. Data indicates that an unconfirmed second planet may lie near the outer asteroid belt. This is a truly fascinating deep sky object because it is so similar to the Earth. It has asteroid belts, it has comets, pretty cool. This slide shows the methods of detection for all of the deep sky object exoplanets. So you can see, going through and just looking at the method of detection, we have, again, radial velocity, transit, 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 pulsar timing, transit, radial velocity, transit, transit, radial velocity. So transit and radial velocity, most of the exoplanets have been observed with those particular methods. There are 3 or 4 other methods, but these are the vast majority. This slide shows all of the exoplanet missions, past, present, currently operating, future. So as you can see, there are the missions that have ended, there are the missions that are still active, and there are those that will be launched, hopefully, in a timely manner. You can go to any of those missions if you want to know more about them. They're all really interesting. This slide is from the Chandra mission. And the Chandra mission hooked up with the European Space Agency's XMM Newton X-ray telescope to map the location of nearby stars to help identify the best targets to search for exoplanets with conditions that are more suitable towards life. Planets that are being bombarded by high-energy X-ray and ultraviolet radiation would damage or destroy any developing atmospheres on any exoplanets. So the most viable exoplanets could now be targeted and directly imaged by future missions, saving them a whole group of exoplanets that most probably are not conducive to life because of the radiation continuously bombarding them. So Chandra looking into the future for exoplanet missions. So let's revisit this summary once again of exoplanets through 2022. You can see up at the top or left, radial velocity 913. Look at transit, 3846. So those are the ones that are the most popular for discovering and studying exoplanets. And here is a summary, a more recent summary that again, if you look at this one, you will see that TESS candidates, there are 7203 candidates integrated into the archive, and the project candidates yet to be confirmed is 4,658. So a lot of exoplanets have been, quote, discovered, but there needs to be some kind of confirmation. So we've discovered really a heck of a lot more exoplanets than we have confirmed. So all is well and good in the world of exoplanets. That was a very brief overview and summary of the deep sky objects for this year. Part 3 coming up, as you see, is going to give an overview of the deep sky objects and their parent stars and their motions and properties. So paragraph 3b in the event description lists the motions and conditions that contribute to the range of exoplanet surface and atmospheric compositions, which help determine the likelihood of habitability and the parameters of the habitable zone. The radial velocity method uses the fact that if a star has a planet or planets around it, it is not strictly correct to say that the planet orbits the star. The planet and the star orbit their common center of mass. Because stars are so much more massive than the exoplanets, the center of mass is within the star, and the star appears to wobble slightly as a planet travels around it. This wobble is measured by using Doppler spectroscopy. If a star is traveling towards Earth, its light will appear blue shifted, and if it is traveling away from Earth, the light will be red shifted. Spectroscopy shows this change in color from a star as it moves towards or away from Earth as it orbits the center of mass of the star-planet system. This method enables calculation of the mass and the orbital period of an exoplanet. This graphic illustrates the transit timing method of detecting exoplanets. The fact that, due from our perspective here on Earth, you can be in a situation where you can watch the exoplanet orbit across the surface of its parent star, be beside it, and then orbit towards the back of it so it's no longer seen. This animation of the illustration in the previous slide shows the orientation of the transit photometry method to provide information about exoplanets. If the orientation of the planet-star system is oriented to Earth so that the planet passes in front of the star, the change in magnitude can be detected. The duration of the partial eclipse is an indication of the size of the planet, and the depth of the partial eclipse is an indication of the size of the star. And again, this is a light curve that is produced because of external factors and not processes ongoing within the star itself. Photometry and spectroscopy of extrasolar planets provides information about their atmospheres and surfaces. Extrasolar planet spectra and photometry, the composition and temperature of the atmospheres, as well as the presence of molecular species and gases, can be inferred. As the light from the parent star filters through the atmosphere of a transiting exoplanet, a small fraction of the light is absorbed by the upper atmosphere of the planet, making the exoplanet appear larger. The degree of atmospheric absorption is dependent on which atomic and molecular species are present, as well as the wavelength of the observations. An example of an Earth-like exoplanet transmission spectrum designed by JWST is on the right-hand side. The link to this description is in the transcript, and JWST gives a really complete and thorough explanation of what kinds of spectra we were looking at to determine exoplanet habitability. Young debris disks can constitute a phase in the formation of a planetary system following the protoplanetary disk phase, when terrestrial planets may finish forming. These disks can also be produced and maintained by collisions between objects such as asteroids and comets. Exoplanets and debris disks can be detected through direct imaging. Interactions of giant planets with the disk produce characteristic signatures, and primary signatures of planets embedded in disks are gaps in young disks and asymmetric density patterns. So, features in disks suggest the presence of full-size planets. Some debris disks have a central cavity, meaning that they are really ring-shaped. The central cavity may be caused by a planet clearing out the dust inside its orbit. Other disks contain clumps that may be caused by the gravitational influence of a planet. The stellar radiation laws and black body radiation have been a part of every past astronomy event, as they explain basic physical properties fundamental to all stars. A black body is an artificial construct that absorbs all radiation it receives and then emits it all away again. Everything that goes in comes out. Stellar atmospheres are very good black body radiators, absorbing radiation produced by the core and emitting it out into the interstellar medium. The hotter the star, the more energy it emits at every single wavelength than a cooler star. The graphic shows a 12,000 K star, a 6,000 K star, and a 3,000 K star. And nowhere does the 3,000 K star emit more radiation at any wavelength than the other two hotter stars. That principle is called Planck's law. Wayne's law states the maximum radiation that comes from any star or black body has a peak with a specific temperature and corresponding wavelength. The mathematical relationship is used to determine the temperature and/or wavelength of stellar objects. The Stefan-Boltzmann law shows that the area beneath the curve is equal to the total power of the star and is related to the temperature and the area of the star. The spectrum on the upper left corner is the optical portion only of the total radiation produced by the sun. There are several absorption lines which show the elemental composition of the sun. The typical spectral images shown in textbooks are gross cartoons of a star's total emission. The other images show spectral plots, wavy lines with dips to show where absorption is happening. Stars are classified by their spectra. and their spectral classification depends upon their temperature. Spectral plots are more useful than images for scientific measurements. Hydrogen Balmer lines and the Fraunhofer lines from other elements are used for classification, and each stellar temperature has a unique set of absorption spectra. The radiation laws and the basic mathematical relationship and equations shown on this slide are the most important for answering the problem sets in this event. All of these equations and relationships have been a part of every NSO astronomy event. The only difference is the addition of the equilibrium temperature equation highlighted in white. The planetary equilibrium temperature is a theoretical temperature that the planet would be at when considered as if it were a black body being heated only by its parent star. The theoretical black body temperature is treated as if it came from an idealized surface of the planet. This calculation can help determine the habitability of the planet. That is a very brief, but there really are not very many, anything in here any more difficult or unusual than it has been every year, except for we are now applying a lot of these methods of detection and stellar properties with exoplanets and their stars. There is only one section left, part 4, which is locating the resources and preparing for how you're going to use the resources and the materials that you have to very successfully prepare. It does not matter whether you are a team that goes to national competition. If you are a team that just does invitationals, you want to do the best that you can in preparing for those particular competitions. So here we go, part 4. Let's look at the resources and the preparation that might help you be successful. This has been a brief overview of the content and deep sky objects for this year's competition. As I said earlier, I have listed links in the transcript that I thought might be helpful. The transcript pages for the deep sky objects are shown on this slide. There are no links on the transcript pages for this last section on resources and preparation because I have placed them all directly onto the slides. NASA's Universe of Learning program, UOL program, supports the space science events for Science Olympiad. From the home page, you can click on resources. From here, you can search on anything for anything on the website that you are looking for. If you click on projects on the resources menu, all of the UOL partnership and projects appear, as you can see on the left-hand slide with the long blue column. Some of them, those partnerships and projects, would be really interesting information for you to look at and collect because it gives several different perspectives on exoplanets that you don't normally see. All of the UOL partnerships and projects appear. You will see Exoplanet Watch, which we're going to be talking about after a bit. And towards the end of the list, you will see the National Science Olympiad. And that's where you can access anything that is relevant to us that we have posted on that site. The Universe Unplugged is part of the Universe of Learning program. And I find it much easier to search, and the information is more appropriate, I think, for our purposes. Scroll down through the home page. You will see a lot of great information and programs. One of the programs is National Science Olympiad Webinars, and that is the site where our stuff is posted. Easier to get to on Universe Unplugged, I think, than going through the Universe of Learning website. So our annual webinars are posted here, as our Reach for the Stars webinar is already posted. This one is going to be posted right behind it. And also, as you can see, any space mission expert talks or presentations are also on this website. The ones that are already up there are very appropriate to exoplanet content. The NASA Exoplanet Travel Bureau is an absolute treasure chest of information. It has excellent full coverage information on every aspect of exoplanets you can imagine. It's great information. Not only is there technical information, but the immersive and search for life menus keep the imagination and fascination alive. It's not all about the data. The JWST website, as well as Hubble, Spitzer, Chandra et al., are great places to learn about exoplanets and the different ways that they observed with all the different wavelengths. The APOD website has always been a good place to search for different images from different missions for stars and other deep sky objects. However, even though it is still supported, I'm afraid that lack of staff and funding is making it a bit difficult to try and keep the information and links updated. So if you're clicking on something that's an older image, one of the links within the paragraph underneath it describing it, a lot of those links aren't going to work anymore. The newer information should still be okay, though. Just a word of warning for that. It's still, when you pull up an object, will give you the most recent images from different wavelengths. And so it still is a useful resource. I hope they can update it as we go along, but funding probably will not improve. And as you can see, the National Science Olympiad website, not only do they have links from their site to the webinars and the talks posted on Chandra, they will also have the transcript for this astronomy presentation. And they also have a lot of other useful links, and they have a store where sometimes you can get a coach's manual, and they are all well worth a few dollars that they cost. So it's another place that you should go looking for resources. On the Chandra website, we have the JS9 image analysis tools posted, along with tutorials and investigations for you to learn how to use those tools. As you can see here on the Chandra website, under education, you will come to the section where they have the webinars for the annual content. You're looking at Connor Todd, who just posted the Reach for the Stars webinar for this year's competition. Oh, and I just have to mention, of course, this is Chandra's 25th anniversary. So it's been a really great mission and produced a lot of incredible discoveries, and we hope it continues to be funded. So this is also the website, when you click on education, that you will access those JS9 image analysis tools. Not only do you access the tools, but there are also tutorials and investigations for you to use to learn the tools. This is the website you will be accessing to answer the JS9 question in the national tournament in 2025. This is the website that hopefully gives you what you need to learn about using JS9. I know that some of you bring binders to competitions instead of laptops. So here's a caveat about JS9. A lot of people do not include JS9 questions. They have not become familiar enough yet with those tools. However, JS9 is not going away. JS9 is the tool that astronomers use. Spectroscopy gives us every single bit of information about every single thing that we know about the universe. It is a powerful and essential tool. And the JS9 questions are not the most difficult questions on this test. If you learn how to use JS9, if you spend some time with it, you will have no problem using the software. Now, if we are lucky enough to get a tournament that has computer labs available, then JS9 will be uploaded and live on the monitors at each station. So all of the teams can answer the JS9 tool at any point that they feel like doing it during the competition. If that is not available, then you will be using your own laptops. So you will be using your individual ones. Now, some of you bring binders and not laptops, and here's we come to that. We used to provide a screenshot version of the JS9 question, and we realized after a while that if you had a binder and you were using the screenshot version, it actually ended up giving you a disadvantage to answering the JS9 question. So we are no longer providing screenshots. For the few of you that come to national competition, and I hope all event supervisors will do this, that they will see that you are loaned a laptop to use during the competition to answer the JS9 question. We are starting to get more and more of these questions into invitationals. They are not for national competition only. They are not for high school competition only. They are not for regional competition only. They are not any more difficult than any other part of the test. I know I'm kind of seem to be blogging here, a pet peeve, but I think that it is really important to learn how to use JS9. It is empowering to use that tool because it is the exact same tool used by scientists. And it isn't just for X-ray observations either. You can load any FITS file from any bandwidth into JS9 and do image analysis with it. So I hope that you learn how to use JS9 and become more proficient with that. Now, it isn't the only place to get JS9 help on how to use it. There is also on the WikiScioli website, which is an interesting website run by students and competitors and science Olympiad teams and people. There's a lot of information there. Some of it's kind of disjointed, but they do a great job trying to keep abreast of all of the competitions that are going on, where you can find sample tests. They will answer questions for you. They're a lot of fun. So there is a section on that. If you click on the Astronomy JS9, do a search for that, up comes this very interesting tutorial. It was actually written by one of my co-event national supervisors for astronomy, Rio Sessions. He is incredibly good with JS9. He and Terry Matilsky wrote the JS9 question for the 2024 competition, and he now has this posted on this website also, and he will also answer questions for you. He's on the contact list at the end of this particular segment. He can answer any specific questions for you about using JS9. It's a whole different approach to JS9. So that one might be more what you're looking for or feel comfortable with than the one on the Chandra website. And another truly interesting application for JS9 we discovered that came from Purdue University. They have a series called Saturday Morning Astrophysics at Purdue. And this particular video that I have here is all about using JS9 to color the universe. It's really interesting. And again, another entirely different approach to using JS9 that might help you become more comfortable. So how do you decide what resources to use? It's not simple. There's a trade-off for everything. So there is, whether you're using online resources, textbook resources, there are things to consider. The breadth or width of the information versus the depth of it, the cost of it, your individual learning style. For online resources, we have listed some for you, some that are the same, some that are a little bit different. If you look down the last one for online resources, you see Google Scholar, because once you get a fundamental understanding of the content and you're ready to go deeper, you're more interested in what's going on way beneath the level at which we are operating, you can go to Google Scholar and look at published research. When you look at published research, you're looking at primary sources. They have interesting research and plots and images and data. The textbook resources that you see listed are some of the better textbook resources. If you look down towards the bottom under online and textbook, the online resources have a wider accessibility. They're all out there. You just have to find them. They're easy to implement. It's easier to find things that fit within your event parameters. There's a broader potential for available sources, though you have to really be careful because a lot of stuff out there is outdated, is inaccurate, is misleading. If you stay within the links that we have given you, I think you're good to go, and I don't think you need any other links unless you want to go deeper with primary resources. The textbook ones, of course, they do have quality. They are reliable. They are organized by topic. If you're someone who learns best sequentially, the content builds upon itself for each topic. And so you end up going greater and greater in depth. One problem, though, with textbooks is the data is 4 or 5 years out of date before the books are published, because unless things have changed a whole heck of a lot, it takes about 5 years to redo an astronomy textbook, such as Astronomy Today, and get a new copy out there. Hopefully, this basic sequence of preparation will help you understand and serve you well for competing. Everybody is different. Everybody has a different learning style, and there are multiple ways to prepare. So as you go along, as you become more and more experienced with competing or just simply taking tests with Science Olympiad, you will determine something that works the best for you and then stick with that. Basically, you're going to read the event description for the content, for the parameters, know what you're allowed to bring to the competition and what you are not, use the webinar and the transcripts for the overview, which you have just done, use the Astronomy Coaches Manual or the Chandra website for basic information. The Astronomy Coaches Manual on the NSO website is actually going to be down a little bit right now. It might need a little bit of revision or reviewing before it goes back up again, but I think it still has value. At least the A team tells me it still has value. I will probably manage to get it up there again fairly soon. So use all of the resources listed in this webinar. Read those Wikipedia. Well, actually, reading the Wikipedia article for each of the topics and DSOs, they do a really decent job with Wikipedia. So you really can learn a lot there. And another thing that you really need to do is take tests. We post some of our initial tests, invitational ones, then sometimes a regional, sometimes a state. We try to keep something up there so that everybody can download them and have the same practice test as those who have the ability to travel for an on-site invitational. We'd like you to have the same experience. We always have something. So go check periodically on the Chandra website and see if we have new things posted. We usually start with something that takes place before December, October, November. So everybody has something early. The Wiki Scioli site, they have tests, they can share. You can write tests for each other. You and your partner can write tests so you can practice with each other. Check around, try to find as many sample tests that you can, because practice is what's going to help you become seriously prepared to take these tests in astronomy and reach for the stars. As you gain more knowledge, again, go into those scientific papers. The abstract and introduction are the most important part, and sometimes they have interesting graphs and images in there too that can be very helpful. It doesn't matter, you won't understand. The first time I read one of those, I didn't understand 95% of what it said, but the more you look at them, the more you read them, the more practiced you become, and the more you learn and the easier it becomes. Read those scientific papers when you get to that level. and spend time with those formulations, the formulas, the relationships, that mathematical part. Understand what they mean, what the relationships are. They are, for the most part, basically simple. The contact information for event updates, materials, and rules clarifications, we have where you can go for Science Olympiad itself, for the science.org Astronomy C. That's where the astronomy resources are posted, and the rules clarification website to answer questions. If you have any question about the event description, the rules, send your question to the clarification committee. Do not send it to us individually. We are not allowed to answer individual questions about the competition itself, about the event description and rules guide itself, because if you send that question to the clarification committee, they will send it to us. And then we will all reply. The Science Olympiad Clarifications Committee will look at all of our replies, formulate one response from them, ask us if this is the correct response, and then they will send it to you. All that is done within 3 days. That way, you all get the same identical answer instead of having, for instance, myself answer the same question to 5 different people and is slightly different. That would be disadvantageous to you. There are now several co-event supervisors for the space science events for astronomy, Reach for the Stars, and solar systems. That's Tad, Connor, Aditya, Robert, Rio, and myself. If you have some kind of question that is not one for the clarifications committee, you can ask us and we will answer you if we possibly can. The essence of the journey is this: practice, practice, practice. If you have access to sample tests from invitationals, find sample tests from invitationals that have been posted, that are on the SciOly Wiki website. Use them, write your own, test each other. It will reinforce the content and the topics every single time you do that. As we've said over and over, question everything. If you don't understand it, look into it. Figure out what you don't understand. Just when we were talking about stellar evolution, you don't memorize the different pieces. You don't memorize the light curves. You don't memorize the sequences that they go through. You don't memorize anything. You integrate it with the other pieces for a grand, higher level understanding of everything. And explore. Many of you are drawn to space science because the topic is inherently wondrous and mysterious. It's beautiful. So nurture that curiosity, and much of the rest of everything else will take care of itself. And as always, may the stars be with you, and we hope you enjoy the journey. Thank you.